All right, folks. So this week we're going to be talking about linear regression, which is going to follow on pretty well from the stuff about scatter plots and correlation. And I'm just going to start, like I always do, by cleaning up my environment, closing all the things that I have open here, and clearing my console so that I don't have any code there distracting me. I'm also going to close this sidebar so that I have the whole space for R, and then I'm going to go find the pre-lab. So that's in the projects folder, and then it's in pre-labs, and then I think it's down at the bottom. It's this one called the regression pre-lab. And if you would like to, you can switch to the visual editor so that you can look at it a little bit more like how it would look when it's knitted. Sometimes I hide away that outline so that I have a little bit more space. It's the same stuff, but it just looks a little nicer. So we're going to set things up the way that we always do by running library mosaic, and we can click the play button on the chunk to run that. And then I cleared out my environment, so I need to reload that example data set that I use every week. So I'm going to put GSS, and then the assignment operator, the less than and the dash, read.csv, parentheses, and then I need quotation marks in there. And then I like using the tab trick, where I hit tab, and then I use the down arrows to get into my data folder, and then it says, okay, there's only one thing in your pre-labs data folder, that's GSS clean. And then I could hit the play button to load in that data. We talked last time about our visualization for two quantitative variables, which would be a scatter plot. So we could look at the relationship between two variables. In this case, I'm looking at the relationship between the highest year of school someone completed and the highest year of school their spouse completed. And that looks roughly linear. It looks like a positive trend. I would probably say that this is a moderate relationship. We could also look at the correlation if we wanted to. A new way that we're going to have to study the relationship between two quantitative variables is a linear model. So we have a function that does this in R. It's called LM, stands for linear model, and it takes the formula syntax that we've been seeing. So it's going to be LM parentheses and then Y tilde X. So whatever you want to predict, tilde, whatever you're using as your predictor. And so if you look at my visualization here, I've got the thing that I'm interested in predicting, the highest year of school completed, that's on the y-axis. And then the thing that I think might explain the highest year of school someone completed, the spouse's education, that's on the x-axis. So when I do my LM, I'm going to have my y variable, highest year of school completed, and then the tilde, and then the one about the spouse. And then at the end, I need to do data equal GSS. So I could just press the play button to run this chunk, and then I get some output. So it says the call, it's just kind of reminding me of the code that I ran. It says I gave it a formula, and here's what I gave it. And then it has the coefficient. So it has the intercept, that's where the line crosses the y-axis. And then the other thing that it gives you is the slope. So the slope for highest year of school completed spouse is 0.594. So this is one way to do a linear model. It's better practice to give your model object a name. So the place where we've seen giving things names before is when we're reading in data. I've been calling my data set GSS, but I could call it Amelia or regression or whatever I want. So I picked out the name GSS, and then I use that assignment operator. We're going to do the same thing with our linear model. I have kind of a dumb naming convention. I usually call my first model that I make in a day M1, and then the second one M2, and the third one M3. You could think of a better name, so like school model would be more descriptive, that would remind you what it's about. But here's how I usually do it. So I have M1, and again, I could have named this model anything I wanted to. I'm going to call it M1, and I use the assignment operator to say, put the result of this LM call into that object called M1. And when I run this, I'm not going to see anything print out, but I'm going to see something new up in my environment. So let's try it. Okay, nothing printed out here, but now I've got this M1 in my environment. it's something you can kind of click on it to look at it, but it's not very easy to see. So the way that we usually look at a model object is with the summary function. So here's how it works. You do summary, parentheses, M1, and then it's going to give you a bunch of information. So I'll run that. Okay, so this is similar to before. It has the call, and it reminds me of the formula. It has some information about the residuals. You can ignore that for right now. It has the same information about the coefficients. So it has that intercept estimate, 5.8474, and it has that slope coefficient in the estimate column, 0.59403. So these are two things that you would want to focus on. There's also lots of other information here. So it tells us our R squared value, it gives the adjusted R squared value, there's p-values for the coefficients. We'll get to that, I think, near the end of the semester. So it gives you tons of information. And then one of the things that we might want to do with this output is to interpret the coefficients in the model. And your professor might have given you a different generic sentence. I have a couple of generic sentences that I prefer, so I'll just show them to you here. So for the intercept, the sentence I like is, if the value of our explanatory variable was 0, our model would predict the response variable to be whatever the value of the intercept is. And then for the slope, I like, for a 1 unit increase in the explanatory variable, our model would predict a slope value unit increase / decrease in the response variable. So let's apply that to this model. So let's see. The intercept number was 5.8, I'll round to 5.85. So the intercept was 5.85. So let's see, I'm going to use this generic sentence. If the value of spouses' years of schooling was 0, our model would predict the years of school completed for an individual to be that 5.85. So if someone's spouse hadn't gone to any school, our model would predict that the person that we were making the prediction for had gone to 5.85, maybe like 6 years of school. They'd done 6th grade. So that's our prediction. So the intercept is, if the explanatory variable is 0, what would the model predict? And then the slope, let's go see what that slope was. I'm going to just round to 0.6. So 0.6 is my slope. And then let's see the sentence. So for a 1, then I need to figure out what the units are in the explanatory variable. In this case, I think they're years. For a 1 year increase in years of spouses' schooling, our model would predict a 0.6, that's our slope value, and then we have to think about the units for the response variable. And in this case, they're years as well. So a 0.6 year, then I have to pick if it's an increase or decrease. So this was a positive slope, so it's going to be an increase. If I'd had a negative sign there, I would have said decrease. A 0.6 year increase in the response variable, which is years of school completed for an individual. So if the spouse's schooling goes up by 1 year, our model would expect the other person's school to go up by 0.6 years. And that kind of makes sense to me. It's kind of close to a 1-to-1 comparison, but it's not exactly a 1-to-1. So that's one thing that we might want to do with a linear model. Something else that we might want to do is to make a prediction. So there's some programmatic ways to do prediction in R, but for now, I recommend you just use R like a big calculator. So if we wanted to make a prediction for this model, I would grab that intercept value, put that in like R as a calculator, and then plus, and I'm going to grab the highest year of school completed, and then I'm going to use the star to mean times and multiply by 12 years of school. So I'm going to have the intercept plus the slope times whatever we're plugging in. And we hit play. Okay, so if the spouse had completed 12 years of school, we'd expect that the individual we're making the prediction for would have done 12.97, around 13 years of school, maybe like 1 year of college. So does that make sense? Yeah, I think so. It makes sense that, people's schooling is pretty similar to one another. And then sometimes we're interested in whether the model is over-predicting or under-predicting a certain point. So we can compute a residual, that's the observed value minus the expected value, and the notation for that is yi minus yi hat. So let's go look at row 21 in our data set. I'm going to click here, and then I'm going to make this big. Let's see, row 21. Okay, respondent 21. They have one child, they're 34. They completed 15 years of schooling. And then how much schooling did their spouse complete? Their spouse completed 12 years of schooling. So if we were going to make a prediction for this person, we'd plug in 12 for their spouse's school, and we would predict that they would have 12.9756, etc. Years of schooling. So if we wanted to do the observed minus expected, we'd say, okay, we observed in the real data that they went to 15 years of school. They did like 3 years of college. And our expected value, our predicted value, is all this stuff. And if I do that subtraction, okay, so 2.02 years. It's a positive residual, which means that we under-predicted. We thought that they would have done less school than they actually did. So if you have a positive residual in this scenario, it means you went to more school than the model expected. And if you have a negative residual, that means you went to less school than the model expected. So that is regression, just as a descriptive technique in R.